Welcome to Deep Science Sleep. Let your eyes grow heavy now, as we begin a gentle journey into the most serene corners of neuroscience. Picture yourself in a dimly lit library, the kind with floor-to-ceiling shelves filled with leather-bound volumes, where dust motes drift lazily through shafts of amber light. You're settled into an impossibly comfortable armchair, wrapped in the softest blanket you can imagine. Outside, rain taps a steady rhythm against tall windows, each drop a tiny percussion note in nature's lullaby. The air smells faintly of old paper and that particular quietness that only exists in spaces dedicated to knowledge and contemplation. Tonight, we're going to explore something extraordinary, something happening right now in this very moment inside your own head. Your brain is performing an elegant dance of deception and protection, a masterwork of filtering that keeps you sane, safe, and surprisingly peaceful. You see, the reality you experience is not reality itself, but rather a carefully curated exhibition, a gentle edit of an overwhelming universe. Your brain is the kindest gatekeeper you'll ever know, deciding what deserves your precious attention and what can safely fade into the background hum of existence. This is not a flaw in your design. This is perhaps the most soothing feature of human consciousness, and understanding it might just change how you see everything around you. The brain as filter, understanding our neural gatekeeper. Right now, as you read these words or listen to this voice, your brain is being absolutely bombarded. Scientists have estimated that approximately 11 million bits of information assault your nervous system every single second. 11 million. That's roughly 1 megabyte of data flooding in through your eyes, your ears, your skin, your nose, your tongue, the proprioceptors in your muscles that tell you where your body exists in space, the vestibular system in your inner ear tracking your balance and movement. It's an incomprehensible tsunami of sensation, a torrent of input that would, if you experienced it all consciously, drive you completely mad within moments. But you don't experience it all, not even close. Of those 11 million bits streaming into your nervous system each second, your conscious mind processes only about 40 to 50 of them. Let that sink in for a moment. Less than 1%, actually far less than 1%. Your consciousness operates on a sliver of available reality so thin it's almost invisible, like trying to understand an entire ocean by examining a single drop of water. This dramatic reduction is not a limitation. It's a gift. It's the work of a remarkable network of neurons tucked away in your brainstem called the reticular activating system, your brain's built-in bouncer, your personal curator of experience. The reticular activating system, often abbreviated as RAS, sits at the base of your brain where your spinal cord begins to blossom into the complex flower of your cerebrum. It's small, barely 2 inches long and half an inch wide, yet it wields enormous power over what you perceive and what simply flows past you unnoticed. Think of the RAS as air traffic control for your consciousness. Imagine an airport where planes are constantly arriving, each one carrying different cargo, different passengers, different levels of importance. Some planes carry urgent medical supplies. Others carry routine mail. Still others are just practice flights, circling without ever needing to land. The control tower, your RAS, must decide which planes get priority to land, which can circle a bit longer, and which should be redirected elsewhere entirely. Without this control tower, you'd have planes crashing into each other, chaos and catastrophe, the complete breakdown of the system. Your reticular activating system performs this triage with breathtaking elegance. It receives input from everywhere. From the spinal cord carrying messages about touch and temperature and pain from your body, from sensory pathways bringing information about sights and sounds and smells, from the thalamus, which is itself a relay station for sensory information, and even from the cortex, the thinking parts of your brain that can tell the RAS what matters based on your current goals and concerns. All of this converges in this tiny bundle of neurons, and decisions get made, faster than thought, about what rises to consciousness and what remains in the shadows. The RAS is composed of 4 main components, each with its own specialty, its own neurotransmitter signature. There's the locus coeruleus in the upper pons, releasing norepinephrine to keep you alert and awake. There are the raphe nuclei scattered along the midline, secreting serotonin to regulate mood and arousal. The posterior tuberomammillary nucleus in the hypothalamus releases histamine, another wakefulness chemical. And the pedunculopontine tegmentum sends out acetylcholine, crucial for the transition between sleep states and wakefulness. Together, these centers create a symphony of activation and inhibition, a complex dance that determines your level of consciousness at any given moment. What makes the RAS particularly peaceful to contemplate is its inherent wisdom. It doesn't just randomly filter. It has developed, through millions of years of evolution and through your own lifetime of learning, an exquisite sensitivity to what matters. When you're at a crowded party with dozens of conversations happening simultaneously, you can focus on the person in front of you, tuning out the background noise. But the moment someone across the room says your name, your attention snaps to them. This is the RAS at work. It's been monitoring everything all along, every conversation, every clink of glass, every laugh, but it only brought to your consciousness what it deemed important. This phenomenon is sometimes called the cocktail party effect, and it reveals something profound about the RAS. It's not that your brain doesn't process all those other conversations. It does at some level. The information comes in, gets analyzed by neural circuits operating below the threshold of consciousness, and most of it gets flagged as irrelevant and discarded before you ever become aware of it. Only when something matches your brain's criteria for importance, like your own name, does it bubble up into conscious awareness. The RAS also handles the gradual process of habituation, one of the most calming features of your nervous system. Habituation is why you stop noticing the hum of the refrigerator after a few minutes in the kitchen, why the pressure of clothes against your skin fades from awareness shortly after you get dressed, why the sound of traffic outside your window becomes invisible to you even though visitors to your home notice it immediately. The RAS learns that these are constant, unchanging, non-threatening stimuli, and it stops bothering your conscious mind with them. It's like a personal assistant who knows not to interrupt you with the same piece of information over and over. The information is still there, still being registered, but it's filed away as background, as the unimportant constancy of your environment. This filtering happens everywhere in your sensory systems, even before information reaches the RAS. Consider vision. Right now, you have a blind spot in each eye, a place where the optic nerve exits the retina and there are no photoreceptors to detect light. You never notice these blind spots because your brain fills them in, inventing information based on the surrounding context. Your visual field is also sharp only in the very center, in the small region called the fovea. Everything in your peripheral vision is actually quite blurry, But you don't perceive it that way because your eyes are constantly making tiny movements called saccades, rapidly scanning the environment to build up a coherent picture. Your brain stitches these fragments together and presents you with the illusion of a clear, complete visual field. The same is true for your other senses. Your ears can only detect sound waves between about 20 Hz and 20,000 Hz. Dogs hear higher frequencies. Elephants communicate with infrasound below our range of detection. The electromagnetic spectrum extends infinitely in both directions beyond visible light, from radio waves stretching kilometers long to gamma rays smaller than atoms. Yet our eyes see only the tiny sliver from about 390 nanometers, violet, to 700 nanometers, red. We're missing most of reality right from the start, limited by the sensors evolution gave us. But here's the beautiful part. We don't need to detect everything. We only need to detect what's relevant for survival, for flourishing, for navigating our particular niche in the world. A bee needs to see ultraviolet patterns on flowers to find nectar. We don't need that, so we don't have it. A bat needs echolocation to navigate in darkness. We don't, so we evolved different capacities. Our filtered reality is not a lesser reality. It's a reality perfectly tailored to being human, to existing in human communities, to solving human problems. It's a customized universe, designed by evolution and refined by learning, to give us exactly what we need and to spare us from being overwhelmed by what we don't. The RAS filters not just based on sensory type or intensity, but also based on meaning and emotional significance. If you're anxious about an upcoming presentation at work, your RAS might become hypersensitive to anything related to that presentation. You'll notice articles about public speaking, you'll overhear conversations about confidence, you'll see posters advertising communication workshops. These things were always there in your environment, but now they're flagged as relevant, so they break through into consciousness. This is why, when you're thinking about buying a particular model of car, you suddenly see that car everywhere. The RAS has been told this is important, so it stops filtering it out. Conversely, when you're feeling safe and calm, the RAS relaxes its vigilance. It becomes less reactive, less likely to interrupt your peace with every minor stimulus. This is the neurological basis for many relaxation techniques. When you practice deep breathing, when you meditate, when you engage in gentle repetitive movements like walking or knitting, you're essentially training your RAS to calm down, to stop treating everything as potentially urgent, to let more of the world flow past without demanding conscious attention. You're teaching your brain's gatekeeper that it's safe to lower the drawbridge, that not every approaching figure needs to be interrogated. Understanding the RAS helps explain why our realities can be so different from each other. Two people can experience the exact same event and have completely different memories of it, not because one is lying or mistaken, but because their brains filtered the event differently. What seemed important to one person's RAS might have been irrelevant to another's. Their attention was drawn to different details, different moments. They literally lived through different experiences, even though they were in the same physical space. This has profound implications for empathy and understanding. When someone describes an experience in a way that seems incomprehensible to you, it might be because their RAS filtered that experience completely differently. Their brain, shaped by different genetics, different past experiences, different current concerns and goals, constructed a different reality from the same raw materials. Neither perception is more correct. Both are valid constructions, each filtered through the unique architecture of an individual nervous system. The RAS also plays a crucial role in sleep and wakefulness, those fundamental rhythms that structure our lives. When you start to feel drowsy in the evening, that's partly because the RAS is reducing its activation of the cerebral cortex. It's beginning to close the gates, to reduce the flow of sensory information allowed into consciousness. Conversely, in the morning, often in response to light hitting your eyes, the lateral hypothalamus releases a neuropeptide called orexin, which activates the RAS, which in turn ramps up stimulation to the cortex, and you wake up. The transition between sleep and wakefulness isn't a simple on-off switch, but rather a dimmer controlled by the RAS, gradually adjusting the flow of awareness. There's something deeply peaceful about knowing that this filter exists, that you're protected from the full onslaught of reality. Your brain is looking out for you every second, making thousands of decisions about what you need to know and what you can safely ignore. It's like having the world's most devoted assistant, one who never sleeps, never takes a break, never stops caring about your well-being. The RAS is always there, quietly curating your experience, letting in just enough stimulation to keep you engaged with the world, but not so much that you're paralyzed by overwhelm. You can work with your RAS rather than against it. If you set clear intentions, if you decide what matters to you, if you clarify your goals, the RAS will adjust its filters accordingly. This is why visualization and goal setting can be powerful. You're essentially programming your RAS, telling it what to watch for. If you decide you want to notice moments of beauty in your day, if you set that intention clearly, your RAS will start flagging beautiful moments for your conscious attention. The same raw reality will present more beauty simply because your filter settings have changed. But you can also give your RAS permission to rest, to filter more aggressively, to protect you from overstimulation. This is what happens in sensory deprivation tanks, in quiet meditation spaces, in the deep forest or by the ocean where the stimuli are fewer and more predictable. With less to filter, with less to monitor, the RAS can relax, and so can you. This is why such environments feel restorative. They're not just psychologically calming, they're neurologically calming, allowing one of the hardest working systems in your body to take a well-deserved break from constant triage. As you settle deeper into relaxation now, you might notice your own RAS at work. The pressure of the surface you're lying or sitting on might fade from awareness. Background sounds that were distinct a moment ago might blur into a gentle wash of white noise. This is your reticular activating system making moment-by-moment decisions, filtering your reality, protecting you from the overwhelming deluge of sensation, and allowing you to rest in the carefully curated calm of your own consciousness. Reality as construction, your brain's predictive powers. Your brain is not a camera. It's not passively recording the world as it passes by. Instead, neuroscience has revealed something far stranger and more wondrous. Your brain is a prediction machine, constantly generating hypotheses about what's out there, testing those hypotheses against incoming sensory data, and constructing your experience from this ongoing dialogue between expectation and evidence. This might sound abstract, so let's make it concrete. Right now, you're reading or hearing these words, and it feels like you're simply perceiving them as they arrive. But actually, your brain is predicting the next word before it appears. It's using its knowledge of language, grammar, context, and your current understanding of the topic to generate expectations about what comes next. When the actual word matches the prediction, you experience a smooth flow of comprehension. When a word is unexpected, there's a tiny surprise, a prediction error that causes your brain to update its model and pay closer attention. Researchers have demonstrated this by monitoring brain activity while people read sentences. If someone reads, "In the hospital, there is a newborn," their visual cortex activates a pattern resembling the word baby before that word actually appears. The brain has made a prediction, and it's so confident in that prediction that it pre-activates the neural circuits associated with the predicted word. This isn't unique to language. Your brain makes predictions about everything. What you'll see when you turn your head, how the chair will feel when you sit down, what sound the door will make when you open it, how your coffee will taste, whether the floor will hold your weight when you step forward. These predictions are based on your entire life history of experiences. Your brain has built up an extraordinarily rich model of how the world works, what statisticians call a generative model, a set of probabilistic rules that generate expectations about sensory input. This model includes physics, objects fall down, not up, biology, living things move in particular ways, psychology, people have intentions and emotions, and countless details specific to your life. The third stair from the bottom creaks. Your friend always arrives a bit late. Rain makes certain petrichor smell. The neuroscientist Carl Friston has proposed what's called the free energy principle to explain this process. The basic idea is that your brain is constantly trying to minimize surprise, to reduce the gap between what it predicts and what actually happens. In information theory terms, surprise is related to entropy or disorder. When something matches your predictions, there's low surprise, low entropy. The world makes sense. When something violates your predictions, there's high surprise, high entropy, and your brain has to work harder to update its model. Minimizing surprise isn't just about understanding the world. It's about survival. An organism that can accurately predict what will happen next has a huge advantage over one that's constantly surprised. If you can predict that the rustling in the grass means a predator might be approaching, you can act before you see the predator. If you can predict which fruits will be ripe and nourishing, you don't have to taste test everything. Prediction allows for proactive behavior, for planning, for anticipating problems before they fully manifest. It's one of evolution's most powerful tools. But here's where it gets really interesting. Your brain doesn't wait for sensory data to come in and then interpret it. Instead, it's constantly streaming predictions downward through the cortical hierarchy, from high-level abstract areas to low-level sensory areas, saying, "This is what I expect to see, this is what I expect to hear." These predictions flow from the top down, from higher brain areas to lower ones. Meanwhile, actual sensory information flows from the bottom up, from sensory receptors through lower processing areas to higher ones. The magic happens when these two streams meet. When the bottom-up sensory data matches the top-down prediction, there's very little activity needed. The brain basically says, "Yes, this is what I expected," and moves on efficiently. But when there's a mismatch, when the sensory data doesn't match the prediction, that's when prediction errors propagate upward, forcing the brain to update its model, to revise its expectations, to pay attention. This is called predictive coding, and there's growing evidence that it's a fundamental principle of how the brain works. You can experience this directly through optical illusions. Consider the famous hollow face illusion. If you see a mask of a face from the inside, so it's actually concave, your brain usually can't perceive it as concave. Instead, you see it as a normal convex face. This is because your brain has such a strong prediction that faces stick outward that it overrides the actual sensory information telling you this face is hollow. The prediction wins over the data. Only when the mask rotates and the conflict becomes too great does the illusion sometimes break. Or think about the dress that went viral online, the one that some people saw as blue and black while others saw as white and gold. This wasn't about people's eyes working differently. It was about their brains making different predictions about the lighting conditions in the photograph. Based on those different predictions about whether the dress was in shadow or in bright light, their brains constructed different color experiences from the same pixel values. The sensory data was identical, but the predictions were different, so the conscious experiences were different. Reality literally looked different to different people. This predictive architecture explains many puzzling features of perception. It explains why you can read text even when the letters are jumbled, as long as the first and last letters are correct. Your brain predicts what the word should be based on context, and it doesn't actually need perfect letter-by-letter information to construct the word in your experience. It explains why you mishear song lyrics, creating bizarre phrases that nonetheless fit the melody and rhythm. Your brain is predicting words that make sense in the context it assumes, and it sometimes fits the wrong words to the sounds. It explains the phenomenon of perceptual set, where what you're expecting to see influences what you actually see. In classic experiments, if people are shown ambiguous figures that could be interpreted as either letters or numbers, they tend to see letters if they've been looking at letters and numbers if they've been looking at numbers. The sensory information is ambiguous, so the brain's predictions, primed by recent experience, determine the conscious perception. The predictive brain explains why sensory deprivation can lead to hallucinations. If you're in an environment with very little sensory input, like floating in a dark, silent sensory deprivation tank, your brain is still generating predictions about what should be there. But now there's very little sensory data to constrain those predictions, to keep them anchored to reality. So the predictions can run wild, creating experiences of light, sound, even complex scenes, purely from the brain's own activity. Hallucinations are, in a sense, predictions that have become unmoored from sensory input. This is why some neuroscientists and philosophers have started describing perception as a kind of controlled hallucination. Even in normal circumstances, what you experience is primarily your brain's prediction about what's out there, only lightly constrained and corrected by actual sensory input. The philosopher Andy Clark calls this the experience machine, emphasizing that your brain is actively constructing your experience rather than passively receiving it. Normal perception is hallucination that's been reined in by sensory data. True hallucination is what happens when that data stops flowing or stops being weighted heavily enough to constrain the predictions. This might sound unsettling at first. If perception is just controlled hallucination, if reality is a construction, what's actually real? But there's something profoundly peaceful in this understanding, too. It means that your experience is not dictated solely by external circumstances. Yes, the external world provides constraints, provides data, but how you experience that world depends heavily on your predictions, which are shaped by your past experiences, your current state, your goals and intentions. You have more agency in your perceptual reality than it might seem. If you can shift your predictions, you can shift your experience. This is why practices like cognitive behavioral therapy can be so effective. They're not changing the external world. They're changing the predictions you bring to bear on that world, the lens through which you interpret events. If you predict that social situations will be threatening, your brain will construct experiences of social anxiety even in objectively safe contexts. But if you can shift those predictions, if you can train your brain to expect safety and connection, the same social situation will be experienced completely differently. The same event, filtered through different predictions, becomes a different experience. Someone who predicts that rainy days are dreary will experience rain as depressing. Someone who predicts that rainy days are cozy will experience the same rain as comforting. The raindrops hitting the window are the same, but the experience is different because the predictive models are different. Your brain is doing this all the time, running simulations, making predictions, comparing them to incoming data, updating models, generating new predictions. It's an endless cycle, happening far too quickly for conscious awareness to track. The computational load is staggering. To predict everything about your environment based on incomplete sensory data requires massive parallel processing, distributed across the entire cortex, with billions of neurons each contributing their piece to the collective prediction. And most of this happens unconsciously. You're aware only of the final product, the experience that emerges when predictions and sensory data have been reconciled. You don't have conscious access to the predictions themselves, to the prediction errors, to the updating process. It's like watching a movie without seeing all the filming, editing, and post-production that went into creating it. You see only the finished product, smooth and seamless, unaware of the enormous computational machinery working behind the scenes. This is actually merciful. If you were consciously aware of every prediction your brain makes, every prediction error it encounters, every model update it performs, you'd be utterly overwhelmed. It would be like trying to watch a movie while simultaneously watching all the footage that was shot, all the scenes that were cut, all the alternative edits that were considered. The finished movie is comprehensible precisely because all that complexity has been hidden, resolved into a single coherent narrative. Your predictive brain is building that coherent narrative every moment. It's taking the blooming, buzzing confusion of sensory data, combining it with the rich predictive models built from your entire life history, and constructing the stable, sensible, mostly predictable world that you experience. When you walk across a room, you don't consciously think about predicting where the floor will be, predicting how your muscles need to contract, predicting how your balance will shift. All of that happens automatically, unconsciously, your brain predicting and adjusting thousands of times per second to create the smooth experience of walking. The peaceful aspect of this is the reliability. Your brain is extraordinarily good at prediction. It's been honed by evolution over millions of years and refined by your personal learning over your entire lifetime. Most of your predictions are accurate most of the time. The world behaves mostly as you expect it to. This creates a sense of stability, of coherence, of understanding. Even though reality is far more complex and chaotic than your conscious experience suggests, your brain's predictive powers create a livable, navigable world. When predictions fail, when you're surprised, that's actually valuable information. Surprise tells you that your model needs updating, that something in the world is different than you thought, that you need to pay attention and learn. This is why novelty can be both exciting and stressful. It's exciting because it offers new information, opportunities to refine your models, to understand the world better. But it's stressful because prediction errors demand cognitive resources. They require you to update beliefs, to modify expectations, to accommodate new information. Too much novelty, too many prediction errors, and you feel overwhelmed, confused, unmoored. But in the right amounts, prediction errors are how you grow and adapt. Every time you're surprised and then figure out why, your brain has improved its model slightly. Over time, these small improvements accumulate into wisdom, into expertise, into a rich understanding of how your particular world works. An expert in any field is someone whose brain has built extraordinarily accurate predictive models in that domain, models refined through thousands or millions of prediction errors, each one an opportunity to update and improve. As you rest now, your brain continues its predictive work, but in a gentler mode. The predictions become less about navigating external challenges and more about maintaining your body's internal state, about cycling through sleep stages, about consolidating memories. The prediction errors that matter in wakefulness, the surprises that demand action, can be safely ignored now. Your brain shifts its focus, turns inward, allows the external world to fade as it engages in the essential work of rest and restoration. The predictive machinery doesn't stop, but it changes its target. Instead of predicting what's out there in the world, it predicts what's needed in here in your body and brain. It predicts and regulates your heart rate, your breathing, your temperature, your hormone levels. These predictions, too, are based on models built from experience, internal models of what your body needs to maintain itself, to heal, to prepare for tomorrow. And these predictions, mercifully, remain mostly unconscious, allowing you to drift peacefully, trusting that your brain knows what to do. The architecture of awareness, sensory limits, and beyond. Before information ever reaches your reticular activating system, before your brain makes its predictions, there's an even more fundamental filtering happening: the limits of your sensory receptors themselves. Your experience of reality begins not with what exists in the world, but with what your sensors can detect. And those sensors, remarkable as they are, have very specific limitations that shape the boundaries of your possible experience. Consider your eyes. They seem to show you the world in full color, in sharp detail, in smooth, continuous motion. But this is an illusion, a construction built from very limited input. Your eyes contain two types of photoreceptors, rods and cones. Rods detect light and dark, providing vision in dim conditions but no color information. Cones detect color but need brighter light to function. You have about 90 million rods but only about 6 million cones, and those cones are concentrated in the center of your retina, in the small region called the fovea. This means that your color vision is actually sharp only in the very center of your visual field, in an area about the size of your thumbnail held at arm's length. Everything else, your entire peripheral vision, has much lower resolution and much poorer color discrimination. But you don't experience it this way because your eyes are constantly moving, making tiny rapid movements called saccades, 3 to 5 times per second, scanning the environment and building up a mental picture from these fragments. Your brain stitches these pieces together and fills in the gaps, creating the illusion of a complete, sharp, full-color visual field. Then there's the matter of what your cones can detect. You have 3 types of cones, each sensitive to different wavelengths of light, roughly red, green, and blue. All the colors you see are constructed by your brain from combinations of these 3 signals. But the electromagnetic spectrum extends far beyond what your cones respond to. Below red, there's infrared, which snakes can see using special pit organs, allowing them to detect the heat signatures of prey in total darkness. Above violet, there's ultraviolet, which bees and birds can see, revealing patterns on flowers and plumage invisible to human eyes. The visible spectrum, the rainbow of colors you can perceive, spans wavelengths from about 390 nanometers, deep violet, to about 700 nanometers, deep red. That's a range of just over 300 nanometers. But the electromagnetic spectrum extends from radio waves thousands of kilometers long to gamma rays smaller than atomic nuclei. The visible portion is a vanishingly thin sliver, less than 1/billionth of the full spectrum. You're seeing 1/billionth of the light that exists, and from that sliver, your brain constructs the entire visual world you experience. The same limitations apply to all your senses. Your ears can detect sound waves from about 20 Hz to 20,000 Hz. This is the range useful for human communication and for detecting relevant sounds in our environment. But elephants communicate using infrasound below 20 Hz, inaudible to human ears, traveling for miles through the ground. Dogs hear ultrasound above 20,000 Hz, which is why a dog whistle is silent to you but piercing to your pet. The full range of acoustic vibrations in the world includes frequencies you will never hear. Your sense of smell relies on receptor proteins in your nose that bind to specific molecular shapes. Humans have about 400 different types of olfactory receptors, which sounds like a lot until you compare it to dogs, who have closer to 1,000. A dog's world is suffused with scents you can't even imagine, chemical signals that pass right through your nose without registering. Your experience of walking through a forest is olfactorily impoverished compared to what a dog experiences in the same forest. Touch seems direct, as if you're truly feeling the world itself. But even here there are filters and limits. Your skin contains different types of mechanoreceptors. Some detect light touch, others detect pressure, still others detect vibration or temperature or pain. But these receptors have thresholds. Stimuli below the threshold don't register. There are gentle touches happening on your body right now. The microscopic movements of air currents, the settling of dust particles, the constant bombardment of photons that you can't feel because they're below your receptors' sensitivity thresholds. Temperature receptors are particularly interesting. You have some that detect warmth and others that detect cold, but neither directly measures temperature. Instead, they detect changes in temperature relative to your skin's current temperature. This is why you can be fooled by touching something that's neither objectively hot nor cold but matches your skin temperature exactly. It seems to have no temperature at all, even though this is physically impossible. Pain receptors, called nociceptors, detect tissue damage or the potential for tissue damage. But pain is not a direct readout of injury. It's a constructed experience, heavily influenced by context, attention, emotion, and expectation. Soldiers sometimes report feeling no pain from severe wounds sustained in battle, their brains suppressing pain signals because survival demands action, not suffering. Conversely, people in chronic pain may experience severe suffering with minimal tissue damage, their nervous systems amplifying signals through neuroplastic changes. All of these sensory limitations mean that the raw material your brain has to work with is already a tiny, filtered subset of what exists. Before any processing, before any predictions, before the reticular activating system makes any decisions, you're already experiencing a customized reality, shaped by the particular sensors evolution gave your species. Different species live in different sensory worlds, even when occupying the same physical space. A dog in your living room experiences a world far richer in smell but poorer in color vision. A cat sees better in dim light but cannot appreciate the full range of colors you see. A bee sees ultraviolet patterns but misses the red wavelengths. Each species has its own umwelt, a term coined by biologist Jacob von Uexküll to describe the perceptual world created by an organism's particular sensory capacities. Your human umwelt is characterized by good color vision, decent hearing across frequencies relevant for speech, mediocre smell, and excellent fine motor control paired with sophisticated touch discrimination in your fingertips. This suite of capacities shapes everything about how you experience reality. You live in a visual world where sight dominates other senses, where you navigate primarily by looking. This isn't universal. Bats live in an auditory world, navigating by echolocation, building mental maps from reflected sound waves. Moles live in a tactile world, their sensitive snouts creating representations of underground tunnels through touch. The information that does make it through your sensory receptors then travels through complex neural pathways before reaching consciousness. Take vision again. Light hits your retina, gets converted into electrical signals by photoreceptors, and those signals pass through multiple layers of processing right in the retina itself, where different types of neurons extract features like edges, motion, and contrast. Only then does the information leave the eye via the optic nerve. That information travels to the lateral geniculate nucleus of the thalamus, a relay station deep in your brain. The thalamus is often called the brain switchboard, receiving sensory information and directing it to appropriate areas of cortex. But the thalamus is not a passive relay. It modulates the information, selectively amplifying some signals and dampening others based on instructions from the cortex and from the reticular activating system. The thalamus is already making decisions about what's important. From the thalamus visual information projects to the primary visual cortex at the back of your brain. Here, neurons respond to specific features. Some fire when they detect a vertical edge, others respond to horizontal edges, still others to particular angles or to motion in specific directions. This feature extraction happens in parallel across millions of neurons, each contributing its piece to the overall analysis. The information then flows forward through a hierarchy of visual areas, each extracting progressively more complex features. Early areas respond to simple features like edges and colors. Later areas respond to combinations of features, to shapes, to objects. Eventually, you get to areas that respond to very specific, complex stimuli. There are neurons that respond selectively to faces, others to places and scenes, others to printed words, others to biological motion. This hierarchical processing transforms the raw pattern of light and dark detected by your retina into the meaningful visual world you experience. Throughout this entire pathway, there's bidirectional communication. Top-down predictions flow backward from higher areas to lower areas, setting expectations. Bottom-up sensory data flows forward, confirming or violating those expectations. The constant interplay between these streams, happening across dozens of brain areas connected by millions of axons, creates your visual experience. The same hierarchical, bidirectional architecture applies to other senses. Sounds detected by your cochlea are processed through multiple areas of auditory cortex, extracting increasingly complex features. Simple tones, then combinations of tones, then phonemes, then words, then sentences, then meaning. Touch information flows from your skin through spinal cord and brainstem to somatosensory cortex, where different areas represent different parts of your body in distorted maps that dedicate more neural real estate to sensitive areas like fingertips and lips. A crucial way station in all of this is the thalamus, that deep structure that receives input from all sensory systems, except smell, which has its own pathway. The thalamus is intimately connected with the reticular activating system and with cortex, forming what's sometimes called the thalamocortical system. This system is thought to be essential for consciousness. When the thalamus is damaged, people can lose consciousness even if their cortex is intact. During deep sleep, the thalamus changes its firing patterns, producing rhythmic oscillations that don't effectively relay sensory information to cortex. This is why you're much less responsive to sounds and other stimuli when deeply asleep. The thalamus has essentially closed the gate, preventing most sensory information from reaching consciousness. You're not unconscious because your sensory receptors stop working. They're still detecting light, sound, touch. You're unconscious because the thalamus is no longer passing that information through to cortex. Anesthesia works partly by suppressing thalamocortical communication. The anesthetic drugs don't just knock out your cortex. They disrupt the coordinated activity between thalamus and cortex, breaking the normal patterns of communication that support consciousness. When the drugs wear off and normal thalamocortical communication resumes, consciousness returns. Another crucial player in the architecture of awareness is the default mode network, a set of brain regions that become active when you're not focused on the external world, when you're daydreaming, remembering the past, imagining the future, thinking about yourself or others. This network includes the medial prefrontal cortex behind your forehead, the posterior cingulate cortex deep in the midline, and the inferior parietal lobes on the sides of your brain. The default mode network is fascinating because it's anti-correlated with networks involved in external attention. When you're focused on a task, on something in the environment, the default mode network quiets down. When you let your attention drift inward, it activates. This network seems to be involved in constructing your sense of self, your narrative identity, the story you tell yourself about who you are. It's active during self-referential thinking, during mind wandering, during that constant inner monologue that chatters away when you're not engaged with external demands. Some meditation practices aim to quiet the default mode network, to reduce the constant self-referential thinking and achieve a state of pure awareness without the overlay of ego. Experienced meditators show reduced activity in the default mode network during meditation, and they report subjective experiences of decreased self-focus, of boundaries dissolving between self and world. This suggests that at least part of what we experience as the self is actively constructed by default mode network activity, not a fixed entity but a process, a story the brain tells. The default mode network also plays a role in mental time travel, your ability to remember the past and imagine the future. These capacities, uniquely developed in humans, depend on being able to construct mental simulations of situations you're not currently in. When you remember yesterday's dinner, you're reconstructing a simulation of that experience using fragments of memory. When you imagine next week's vacation, you're constructing a simulation using knowledge and imagination. Both involve the default mode network assembling details into coherent scenarios. This is another form of prediction, really. Your brain is constantly simulating possible futures, running mental models of how situations might unfold, allowing you to plan and prepare. These simulations are predictions stretched into the future, tentative stories about what might happen, used to guide current decisions. Your brain is not just predicting the next moment. It's predicting hours, days, years ahead, constructing possible futures and evaluating them, all beneath the surface of conscious awareness. Language areas, tucked in the left hemisphere for most people, add another layer of filtering to your experience. Language allows you to categorize and label your experiences, to communicate them to others, to think about them abstractly. But language also limits what you can easily conceptualize. If your language doesn't have a word for a particular distinction, that distinction is harder to think about, harder to remember, harder to communicate. The words available to you shape the thoughts available to you. This doesn't mean you can't think thoughts for which you have no words. You can. But named concepts are easier to work with, easier to recall, easier to share. This is why learning new words, new distinctions, can genuinely expand your mental world. When you learn the word petrichor for the smell of rain on dry earth, you might start noticing that smell more, savoring it, distinguishing it from other rain-related smells. The label helps the experience crystallize, become more vivid, more available. All of these systems, sensory receptors, thalamus, cortical hierarchies, reticular activating system, default mode network, language areas work together to construct your conscious experience. It's a massively parallel, distributed process with information flowing in all directions simultaneously. Bottom up from senses, top down from predictions, laterally between cortical areas, reciprocally between cortex and subcortical structures. The resulting experience feels unified, seamless, immediate. You don't perceive all this complexity. You just see the world, hear sounds, feel sensations, think thoughts. The computational machinery running behind the scenes is completely invisible to conscious introspection. This is efficient. If you had to consciously manage all these processes, you'd never be able to function. The fact that it's all automatic, that it all happens without your intervention, is what allows you to focus your limited conscious capacity on what matters. Making decisions, forming intentions, directing action. And there's something peaceful in recognizing this architecture, in understanding that you are not separate from these processes, but rather you are these processes. Your consciousness is not a little person sitting inside your head watching the show. It is the show, the emergent result of all these neural systems working together. There's no homunculus, no ghost in the machine. There's just the machine, gloriously complex, creating the phenomenon of you experiencing the world from inside your skull. Dreams, sleep, and neuroplasticity. Every night, as you drift into sleep, your brain embarks on one of its most mysterious and essential journeys. For roughly a third of your life, you will be unconscious, unresponsive to the outside world, engaged in a process so critical that deprivation from it for even a few days creates profound physical and mental deterioration. Sleep is not simply rest. It's active, purposeful, restorative in ways that neuroscience is only beginning to fully understand. And woven throughout sleep are dreams, those bizarre nighttime hallucinations that have puzzled humans since the dawn of self-awareness. Why do we dream? Theories abound. Some have suggested dreams process emotions, helping us work through the psychological residue of daily life. Others propose dreams consolidate memories, deciding what to keep and what to discard. Still others see dreams as random neural firing, noise in the system to which our narrative-hungry brains assign meaning. But recent neuroscience has offered a particularly elegant explanation, one rooted in neuroplasticity and the unique challenges posed by sleep itself. David Eagleman, a neuroscientist specializing in neuroplasticity, has proposed what he calls the defensive activation theory. The theory starts with a simple observation. When you sleep, your eyes are closed. You're not receiving visual input. For the 8 hours or so that you're asleep, your visual cortex, which normally processes the constant stream of light information from your eyes, receives nothing. That's a problem. Your brain is highly plastic, especially in development but continuing throughout life. Neuroplasticity is the brain's ability to reorganize itself, forming new connections between neurons and modifying existing ones in response to experience. When a brain area receives regular input, it maintains its function and connections. But when input stops, neighboring areas can invade, taking over and use territory for their own purposes. This is called cortical takeover, and it happens remarkably quickly. Studies have shown that if you blindfold sighted people for just 5 days and give them intensive braille training, their visual cortex starts responding to touch. In people who lose their vision permanently, the visual cortex is eventually recruited by other senses, particularly hearing and touch. The brain doesn't let valuable neural real estate sit unused. If one sense isn't using it, other senses move in and take over. This poses a problem for sleep. Every night, vision stops for hours. If the visual cortex were truly idle during that time, you'd expect other senses to start invading, taking over visual cortex for auditory or somatosensory processing. You'd have to relearn vision every morning, as your visual cortex got reclaimed from these nightly invasions. Clearly, this doesn't happen. But why not? The defensive activation theory proposes that dreaming is the solution. During REM sleep, the stage where most vivid dreaming occurs, your visual cortex is highly active, even though your eyes are closed and sending no visual information. This activity, driven by internal signals from deep brain structures, keeps the visual cortex engaged, defending its territory from potential takeover by other sensory systems. Dreams are the visual cortex's way of staying in shape, of maintaining its visual function during the long hours when there's no visual input from the outside world. Supporting this theory is the observation that species with greater neuroplasticity spend more time in REM sleep. Animals whose brains are more flexible, who have longer developmental periods and more learning capacity, also have more REM sleep. Conversely, animals with more pre-programmed brains, who develop quickly and have less neural flexibility, have less REM sleep. This suggests a link between the need to defend plastic brain regions and the amount of REM sleep required. In humans, REM sleep is distributed throughout the night, occurring roughly every 90 minutes in cycles that grow longer toward morning. During REM, your brain becomes almost as active as when you're awake. Your eyes move rapidly beneath closed lids, giving the stage its name. Your muscles become paralyzed, a protective mechanism called REM atonia that prevents you from acting out your dreams. Your heart rate and breathing become irregular. Your brain consumes about as much energy as during wakefulness, processing nothing from the external world but generating vivid internal experiences. What you experience during REM is often bizarre. Dreams blend impossible physics, sudden scene changes, emotional intensity without clear cause, narrative incoherence. People from your past appear in present contexts. You have abilities you don't actually have. Time moves strangely, compressing hours into moments or stretching seconds into ages. This bizarreness might reflect the fact that dreams are generated without external sensory constraints. The visual cortex is active, creating visual experiences, but those experiences aren't anchored to actual photons hitting your retinas. They're pure construction. Predictions run wild without sensory data to constrain them. Despite their strangeness, dreams often have a visual richness and clarity that rivals or even exceeds waking vision. You see colors, recognize faces, navigate spaces, all with remarkable detail. This supports the idea that dreaming serves to keep visual processing sharp. If dreams were just noise, you wouldn't expect such detailed, coherent visual experiences. The fact that they're visual at all, that they activate visual cortex and generate visual qualia, suggests they're doing something specifically for vision. But REM sleep and dreaming are not the only important sleep stages. Sleep architecture includes several distinct stages, each with different brain activity and different functions. Non-REM sleep includes 3 stages, ranging from light sleep to deep slow-wave sleep. In deep sleep, your brain produces high-amplitude, low-frequency delta waves, synchronized oscillations that sweep across the cortex like slow ocean swells. Deep sleep appears to be crucial for memory consolidation and synaptic homeostasis. During waking hours, your brain forms new synaptic connections as you learn and experience the world. These connections strengthen memories, encode skills, represent knowledge. But if this strengthening continued unchecked, synapses would eventually become saturated, unable to encode new information efficiently. You'd run out of room for new learning. The synaptic homeostasis hypothesis, proposed by neuroscientists Giulio Tononi and Chiara Sorelli, suggests that sleep, particularly deep non-REM sleep, globally downscales synaptic strength. While you're awake, synapses are selectively strengthened by experience. During sleep, there's a global weakening, a pruning process that brings overall synaptic strength back down while preserving the relative differences that encode information. Synapses important for memory remain relatively strong. Less important ones are weakened more. The overall effect is like clearing a cluttered room, making space for new things while keeping what matters. This downscaling is not just theoretical. Researchers have measured changes in synaptic size and strength across the sleep-wake cycle in animals, finding exactly the pattern predicted by the hypothesis. Synapses grow during waking, shrink during sleep. This isn't forgetting. It's optimization, removing the noise to clarify the signal, strengthening important connections relative to unimportant ones. Sleep also appears critical for memory consolidation, the process of transforming fragile, temporary memories into stable, long-term ones. During sleep, particularly during the transition from light sleep to deep sleep, your brain replays patterns of activity from waking experiences. Neurons that fired together during learning fire together again during sleep, often in compressed, accelerated sequences. This replay seems to transfer information from the hippocampus, where memories are initially encoded, to the cortex, where they're stored long-term. You can see this in studies where people learn a task before sleeping. Those who sleep show better retention and even improvement in the task compared to those who stay awake. The improvement is not just less forgetting. People sometimes get better at a skill after sleeping on it, as if the brain has been practicing overnight. This offline improvement suggests that sleep is doing active work, refining and strengthening neural circuits related to learning. REM sleep also contributes to memory, but in different ways than non-REM. REM appears particularly important for emotional memory processing. The hippocampus, which is active during non-REM replay, is less active during REM. But areas like the amygdala involved in emotional processing are highly active. This has led to theories that REM sleep helps process emotional experiences, integrating them into memory while reducing their emotional intensity. There's evidence that REM sleep can help with emotional regulation. People deprived of REM sleep show increased emotional reactivity and difficulty regulating negative emotions. Conversely, a good night's sleep, including adequate REM, can make yesterday's frustrations seem less overwhelming. The phrase "sleep on it" captures folk wisdom that neuroscience is confirming. Sleep, particularly REM sleep, helps you gain perspective on emotional events. Dreams during REM might serve this emotional processing function. The amygdala reactivates emotional memories, but in the strange, safe context of dreams, where real-world consequences don't apply. You might dream about threatening situations, but you're safe in bed, your body paralyzed so you can't harm yourself, your rational mind offline so you don't realize it's just a dream and prematurely wake up. This might allow your brain to rehearse emotional responses, process difficult experiences, without the full intensity of waking emotional reactions. Some researchers have started using this insight therapeutically. Nightmare disorder, common in people with PTSD, can be treated with imagery rehearsal therapy, where you consciously rewrite a nightmare while awake, giving it a new, less threatening ending. Practicing this new version during the day can change the dream at night, presumably by altering the predictions your brain brings to bear on the emotional memory being processed during REM. Sleep also supports neurogenesis, the birth of new neurons, particularly in the hippocampus. While neurogenesis continues throughout life, it's promoted by sleep and suppressed by sleep deprivation. New neurons integrate into existing circuits, potentially supporting new learning and cognitive flexibility. Chronic sleep deprivation can reduce neurogenesis, which may contribute to the cognitive impairments seen with inadequate sleep. The glymphatic system, a waste clearance pathway in the brain, becomes more active during sleep. Metabolic waste products, including proteins like amyloid beta that accumulate in Alzheimer's disease, are flushed out more efficiently when you're asleep. The spaces between brain cells actually expand during sleep, allowing better flow of cerebrospinal fluid through the tissue, washing away cellular debris. This suggests that sleep is a time of physical cleansing, removing toxic buildup that accumulates during waking activity. All of these functions, synaptic homeostasis, memory consolidation, emotional processing, neurogenesis, waste clearance, happen largely unconsciously. You're not aware of your brain replaying daytime experiences, pruning synapses, generating dreams to defend visual cortex, flushing out waste proteins. You just sleep and wake feeling restored, with yesterday's events integrated into memory, emotions processed, brain cleared of accumulated metabolic debris. There's something profoundly peaceful about this understanding. Sleep is not lost time. It's not unproductive. Your brain is working incredibly hard while you sleep, performing essential maintenance that cannot happen while you're awake and actively engaging with the world. The unconsciousness of sleep allows processes that would be impossible during waking, when your brain is busy with perception, action, thought. Dreaming, rather than being meaningless noise or psychological symbol decoding exercises, serves concrete neuroscientific functions. Your bizarre nighttime visions are keeping your visual system operational, processing emotions, perhaps even solving problems through novel combinations of stored knowledge freed from waking logic. The strangeness of dreams reflects the brain's freedom during sleep to run simulations unconstrained by sensory reality, to explore possibility spaces, to maintain and refine neural systems. As you prepare to sleep now, you can rest easy knowing that your brain has elaborate mechanisms in place to take care of you through the night. The sleep stages will cycle naturally, each serving its purpose. New neurons will integrate into hippocampal circuits. You will wake restored, refreshed, with a brain that has spent the night maintaining and optimizing itself, preparing for another day of experience and learning. The peaceful power of perception. Visual illusions reveal something profound about how your brain constructs reality. They're not just quirky tricks or fun puzzles. They're windows into the predictive, constructive nature of perception, moments when we can catch the brain in the act of making its best guess rather than passively receiving information. And there's something strangely calming about recognizing that what you see is not what's there, but rather what your brain predicts should be there based on limited information and lots of assumptions. Consider the Knizia triangle, a classic illusion where three Pac-Man-like shapes are arranged to suggest a triangle even though no triangle is actually drawn. Your visual system sees the triangle so clearly that it's hard to believe it's not there. But if you analyze the image objectively, there are only three incomplete circles and a few lines. The triangle is pure construction, added by your brain because that's the most probable interpretation of the arrangement. A patient known in the literature as became blind early in life from cataracts and had his vision surgically restored as an adult. When shown the Knizia illusion, he could not see the triangle. The illusory shape that seems so obvious to those of us with lifelong vision was invisible to him. This suggests that seeing the triangle requires having built up, through years of visual experience, strong predictions about how objects occlude each other, how boundaries work, how surfaces are arranged in three-dimensional space. Hadn't built those predictions, so his brain didn't construct the triangle. This tells us something crucial. Much of what you see is predicted based on your accumulated visual experience, not directly given by the pattern of light entering your eyes. The Knizia triangle demonstrates that your brain actively creates contours, surfaces, and objects that help make sense of the visual information, even when those contours aren't physically present. Or consider the hollow face illusion, where a concave mask of a face appears convex. Your brain has such strong predictions that faces stick outward that it literally inverts your perception, making the hollows appear as bumps. The sensory information clearly indicates concavity, but your predictions override the data. This can persist even when you know intellectually that the face is hollow. Knowledge doesn't always change perception because perception is driven by unconscious predictions, not conscious reasoning. Color is another realm where illusions reveal construction. The famous dress that appeared blue and black to some viewers and white and gold to others demonstrated that color perception depends on assumptions about lighting. Your brain must solve a difficult problem. The light reflected from an object to your eye depends both on the object's actual color and on the color of the light illuminating it. To perceive the object's true color, your brain must discount the illumination. Different people apparently made different assumptions about whether the dress in the photograph was in shadow, making them perceive it as white and gold, their brains compensating for blue-tinted shadow, or in bright light, making them perceive it as blue and black. The pixel values were identical, but the inferred illumination was different, leading to radically different color experiences. Two people looking at the same image literally saw different colors, not because their eyes worked differently, but because their brains made different predictions about the lighting conditions. The checker shadow illusion, created by Edward Adelson, is another stunning demonstration. Two squares on a checkerboard, one in shadow and one in light, appear dramatically different in brightness. One looks dark gray, the other light gray. But if you measure the actual light intensity they're reflecting, or if you cut them out and place them side by side, they're identical shades of gray. Your brain has corrected for the shadow, making the square in shadow appear lighter than the identical square in bright light, because your brain predicts that surfaces in shadow should appear darker and compensates accordingly. These illusions might seem like failures of perception, errors in the system, but they're actually the inevitable consequence of a system that works through prediction and inference. Your brain is solving an impossible problem, reconstructing a three-dimensional world from two-dimensional retinal images, figuring out object colors from wavelengths that depend on both object and illumination, identifying objects that might be partially hidden or viewed from unusual angles. There's no way to do this reliably based solely on the sensory data. The data is ambiguous, insufficient, so your brain makes educated guesses, predictions based on how the world usually works. Most of the time, these predictions are correct. Faces usually stick outward. Objects usually cast shadows. Surfaces continue behind occluding objects. Colors stay constant under different lighting. The visual world is usually coherent and predictable. So your brain's assumptions, its predictive strategies, work brilliantly in normal circumstances. The illusions happen when reality violates those assumptions, when a face actually is hollow, when identical shades appear in different lighting contexts, when arrangements of shapes suggest objects that aren't there. There's something deeply peaceful about recognizing that you live in a world of your brain's making. Not that external reality doesn't exist, it does, and it provides constraints and corrections to your predictions. But what you experience is a simulation, a controlled hallucination, a best guess about what's out there based on fragmentary evidence and a lifetime of learned predictions. This simulation usually matches reality closely enough for you to navigate effectively. When it doesn't, you get illusions, mistakes, surprises. And those surprises are opportunities to update your predictions, to refine your model of the world. Your brain is constantly filling in gaps, constructing coherence from fragments. You have a blind spot in each eye where the optic nerve exits the retina, yet you never notice a hole in your vision because your brain fills it in based on surrounding context. Your peripheral vision is extremely poor, yet you experience a sharp, detailed visual field because your eyes are constantly moving and your brain is stitching fragments together. During eye movements, you should see a blur, but you don't because your brain edits it out. Each blink should create a visible gap in vision, but doesn't because your brain maintains perceptual continuity across the interruption. This editing, this construction, this gap filling is happening constantly, seamlessly, invisibly. You're not aware of it because the final product is what reaches consciousness. A coherent, stable, mostly accurate model of your environment. The enormous computational work happening behind the scenes to create that model remains unconscious, automatic, effortless from your perspective. Motion perception offers another window into prediction. When you track a moving object with your eyes, you can follow it smoothly, your brain predicting its trajectory and moving your eyes to match. But this prediction has lag. The visual information takes time to travel from retina to cortex, time to be processed, time to influence motor commands. If your eyes depended only on actual sensory input, they'd always lag behind a moving target. So your brain predicts where the object will be slightly in the future and directs your eyes there. For smoothly moving objects, this prediction is accurate, and you can track effortlessly. But if an object moves erratically, unpredictably, the predictions fail, and your eyes jump around and catches up saccades rather than smooth pursuit. Your subjective experience is that tracking smooth motion is easy while tracking jerky motion is hard, but the real difference is in how well your brain can predict the motion. There's even evidence that much of what you experience as now is actually slightly in the past, a constructed present assembled from sensory inputs that arrived at different times. Sound travels much slower than light, so when you watch someone speaking from across a room, the visual information arrives slightly before the auditory information. Yet you perceive their lips moving in perfect sync with their voice. Your brain is adjusting the timing, delaying the faster visual signal to match the slower auditory signal, creating the perception of synchrony. This constructed present extends about 80 to 100 milliseconds into the past. Your now is actually a backwards-looking summary of the very recent past, assembled by your brain to create coherent, synchronized experience from inputs that arrive at different times through different channels. You're living slightly in the past, experiencing a world your brain has already processed and edited, but perceiving it as the present moment. Habituation, the process where repeated stimuli fade from awareness, is another form of prediction. When a stimulus first appears, it's novel, unpredicted, generating prediction error. Your brain pays attention, processes it fully, updates its model to include this new stimulus. But once the stimulus is incorporated into your predictions, once your brain expects it, it generates less prediction error and requires less conscious attention. The humming refrigerator becomes inaudible. The pressure of clothing fades. The smell of your own home disappears while visitors notice it immediately. This is not sensory adaptation, not your receptors becoming less sensitive, though that happens too. It's higher-level filtering, your brain deciding that constant, unchanging stimuli aren't worth conscious attention. This allows you to focus on what's new, what's changed, what might require response. Sufficient, protective, calming. Imagine if you couldn't habituate, if every sensation remained as vivid and demanding of attention as when it first appeared. You'd be overwhelmed, unable to focus on anything because everything would be equally present. The flip side of habituation is sensitization, where repeated exposure to significant stimuli increases responsiveness. If a sound is associated with danger, Repeated exposure makes you more sensitive to it, not less. This might seem to contradict habituation, but it makes sense in terms of prediction and prediction error. Habituation occurs when stimuli are predictable and irrelevant. Sensitization occurs when stimuli are predictable and important. Your brain learns what matters and adjusts its filtering accordingly. Pattern recognition, one of your brain's superpowers, also relies on prediction. You can recognize objects from partial information, faces from just eyes or just mouth, words from jumbled letters. Your brain has stored templates, patterns learned through experience, and it matches incoming information against these templates. When there's enough of a match, even with incomplete or degraded information, recognition occurs. You predict the whole from the part. This is why you can read text even when letters are missing or replaced, why you can understand speech even with background noise, why you can recognize friends from their silhouettes or gait. Your predictions fill in what's missing, completing patterns based on learned templates. The more familiar a pattern, the less information you need to recognize it. Experts in a domain can perceive structure that novices miss because experts have built up rich, detailed templates that allow recognition from minimal cues. There's something meditative about recognizing that your moment-to-moment experience is this constructed simulation, this controlled hallucination that usually but not always matches external reality. It takes pressure off the notion that you should be perceiving things correctly, that there's one true way to see the world. Different brains with different experiences will construct different perceptual realities from the same sensory input. Neither is more correct. Both are valid attempts to make sense of ambiguous information using the predictions available. This understanding can cultivate humility and empathy. When someone describes an experience differently than you would, when they seem to see something you don't or miss something you notice, it's not necessarily that one of you is wrong. You might simply be bringing different predictions to bear, constructing different perceptual realities from the same stimulus. Recognizing this can reduce conflict, increase understanding, allow space for multiple valid perspectives on the same situation. As you sink deeper into relaxation, you might notice the constructed nature of your own perception. The room around you, the sounds you hear, the sensations in your body, all of it filtered, predicted, constructed by your brain from limited sensory input and a lifetime of learned expectations. And there's peace in this recognition, in understanding that the brain's job is not to show you objective reality, but to create a functional simulation that helps you navigate effectively. That simulation is working right now, creating the experience of this moment, this gentle drift towards sleep, this peaceful awareness dissolving into the restorative unconsciousness that awaits. Language, concepts, and edited reality. Language is one of humanity's greatest achievements, allowing us to share thoughts, coordinate actions, build cumulative culture, and think in ways impossible without symbolic representation. But language is also a filter, shaping and constraining what we can easily think about, remember, and communicate. The words available to you influence the concepts available to you, the distinctions you naturally make, the categories you use to organize experience. Consider the simple act of naming a color. Different languages divide the color spectrum differently. Some languages have separate words for light blue and dark blue, treating them as fundamentally different colors like English treats blue and green. Speakers of such languages are faster at distinguishing light and dark blue, suggesting that having separate words makes the distinction more salient, easier to perceive and remember. Other languages have a single word for both blue and green, and speakers may not naturally make the distinction English speakers take for granted. This doesn't mean speakers of different languages see colors differently in terms of raw sensation. Their eyes work the same way, but the categories they habitually use to think about color are shaped by their language. A Russian speaker is more likely to notice and remember the difference between light and dark blue because Russian makes a linguistic distinction there. An English speaker is more likely to notice and remember the difference between blue and green because English makes that distinction. This extends far beyond color. Some languages have elaborate vocabularies for kinship relations, distinguishing maternal and paternal relatives, older and younger siblings, relatives by blood versus marriage in ways English doesn't. Speakers of such languages naturally attend to and remember these distinctions. Some languages lack specific numbers above 2 or 3, using words that roughly mean several or many for larger quantities. Speakers of such languages may struggle with exact numerical tasks that seem trivial to speakers of languages with precise number words. Time concepts vary across languages. Some languages require speakers to specify whether they witnessed an event directly or heard about it from others, embedding evidentiality into the grammar. This makes speakers constantly attend to and remember the source of information. Other languages require specification of tense and aspect, whether an action is completed or ongoing, happened once or repeatedly. Still others treat time more spatially, talking about the future as ahead or behind in different ways, which influences how speakers think about time's direction. The linguist Benjamin Lee Worf famously proposed that language determines thought, that speakers of different languages literally think differently because their languages provide different conceptual structures. This strong form, called linguistic determinism, is probably too extreme. People can think thoughts for which they lack words, can learn new concepts from other languages, can think non-linguistically using imagery or other modalities. But a weaker form called linguistic relativity is well-supported. Language influences thought. The categories and distinctions your language makes readily available are easier to think with, easier to remember, easier to notice in perception. Language doesn't prevent you from making other distinctions, but it makes some more natural, more automatic, more frequently used. When you learn a new word, especially one that captures a concept you'd noticed but never named, there's often an aha moment. The Japanese word kamaribi describes sunlight filtering through tree leaves. The German schadenfreude captures pleasure at others' misfortune. The Danish hygge evokes a particular quality of cozy contentment. Learning these words doesn't create the experiences they describe. You've probably felt all these things. But having a word makes the concept more solid, more discussable, easier to recognize and cultivate. Language also shapes thought through metaphor. Many abstract concepts are understood through metaphorical mapping from concrete domains. Time is often conceptualized spatially. Events are ahead or behind. Time passes. Deadlines approach. Emotions are often conceptualized as containers or forces. You're filled with joy, bursting with pride, overcome by sadness. These metaphors aren't just decorative language. They structure how you actually think about these abstract domains. The linguist George Lakoff and philosopher Mark Johnson have documented hundreds of these conceptual metaphors, showing how they shape reasoning. If you think of argument as war, with metaphors like defending a position, attacking claims, winning or losing, you approach discussions differently than if you think of argument as collaborative exploration. The metaphor frames the concept, influencing behavior and attitude. Schemas, mental models, or frameworks for understanding situations are closely tied to language. When you hear restaurant, a whole script activates. Entering, being seated, receiving a menu, ordering, eating, paying, leaving. This schema guides perception and behavior. You know what to expect, how to act. When you encounter a new restaurant, you don't start from scratch. You apply the restaurant schema, adjusting only for specific differences. Language crystallizes these schemas, allows them to be named and shared. Going to a restaurant invokes the schema in others. They know what you mean, what to expect, how to prepare. Without language, you might still have behavioral routines for recurring situations, but they'd be harder to communicate, harder to reflect on, harder to modify deliberately. Schemas can be limiting, though. They create expectations that bias perception. If you have a schema for bad neighborhood, and you're in a place labeled that way, you might perceive threat even in neutral behaviors. If you have a schema for genius and meet someone with that reputation, you might interpret ordinary comments as profound. The schema filters reality, making you attend to schema-consistent information and miss schema-inconsistent details. The reticular activating system interacts with schemas and language in shaping what reaches awareness. If you have strong schemas, clear categories, precise vocabulary for a domain, your RAS will be attuned to relevant stimuli in that domain. A birdwatcher notices birds others miss because they have schemas and vocabulary for bird types, behaviors, habitats. Their RAS has been trained through learning to flag bird-related stimuli as important. This is why expertise changes perception. Experts don't just know more facts. They literally see differently. A chess master glances at a board and immediately perceives patterns, threats, opportunities that are invisible to novices. Their RAS and perceptual systems have been trained through thousands of hours to recognize meaningful patterns. The sensory input is the same, but the constructed experience is radically different. Language also plays a role in the construction of social reality, aspects of the world that exist only because we collectively agree they do. Money has value because we agree it does. Borders separate nations because we agree they do. Marriage binds people because we agree it does. These social realities are real in their effects. They shape behavior, create obligations, distribute resources, but they don't exist independently of collective belief and linguistic convention. The philosopher John Searle has written extensively about social reality, distinguishing it from brute physical facts. A mountain exists whether or not anyone thinks about it. But a border between countries exists only through collective agreement, typically enshrined in language through treaties, laws, and maps. This doesn't make borders less real in practical terms. They have enormous real-world consequences. But it highlights that much of human reality is linguistically and conceptually constructed. Your sense of self is partly a linguistic construction. The story you tell yourself about who you are, what you value, where you're going, is necessarily told in language. The categories you use to describe yourself, introvert or extrovert, creative or analytical, ambitious or content, are linguistic, and they shape how you interpret your behavior, make decisions, present yourself to others. If you describe yourself as shy, you might decline social invitations differently than if you describe yourself as selective about social energy. The default mode network, which we discussed earlier, is heavily involved in self-referential thought, in constructing and maintaining narrative identity. This network is interconnected with language areas, suggesting that the linguistic self-story and the neural self-representation are closely intertwined. When you think about yourself, you're typically using language, even if silently, even if abstractly. The words you use to think about yourself matter. Negative self-talk, repetitive self-critical narratives can become self-fulfilling through this mechanism. If you constantly tell yourself you're bad at something, your RAS will notice and remember instances that confirm this belief while overlooking instances that contradict it. The belief shapes perception, which confirms the belief, creating a feedback loop. Cognitive behavioral therapy works partly by helping people identify and modify these linguistic patterns, changing the language they use to interpret events and describe themselves. Positive affirmations, while sometimes mocked, can work through similar mechanisms. By repeatedly articulating a desired belief, you're training your RAS to notice evidence for that belief. This doesn't work magically. You can't just affirm something completely contrary to reality and have it become true. But for beliefs that are held more by habit than by strong evidence, changing the linguistic framing can shift the perceptual filtering, which can then shift the accumulating evidence, which can eventually shift the belief. Language allows abstraction, the ability to think about categories rather than specific instances, to reason about general principles rather than concrete cases. This is incredibly powerful. You can learn from one example and apply that learning to infinitely many cases by abstracting the principle. But abstraction can also distance you from direct experience. When you label an emotion, you might feel it less intensely. When you categorize an experience, you might miss its unique details. Some meditation practices emphasize prelinguistic awareness, trying to experience reality more directly, without the layer of conceptual categorization that language imposes. This doesn't mean rejecting language or thinking it's bad, but it recognizes that language is one mode of engaging with reality, and temporarily stepping outside it can offer different insights, can reveal aspects of experience that linguistic categorization obscures. The breath, for instance, can be experienced as a direct sensation. Coolness in nostrils, expansion of lungs, movement of belly, or it can be categorized and labeled. I'm breathing, this breath is shallow. My breathing is anxious. The sensation itself is prelinguistic. The labeling adds a layer of interpretation. Sometimes dropping that layer and just experiencing the raw sensation can be calming, can quiet the constant mental chatter that language enables. Language is one of the most sophisticated filters your brain uses to edit reality. It highlights certain distinctions, obscures others, enables certain types of thought while making others more difficult. It allows unprecedented complexity of communication and reasoning while also potentially limiting what you can easily conceive. And it's deeply woven into your sense of self, your schemas, your predictions, your filtered experience of reality. Understanding language as a filter, rather than a transparent window onto reality, can create some mental flexibility. You can learn new words, new concepts, new ways of categorizing experience, and in doing so expand your mental world. You can recognize that different languages, different vocabularies, different conceptual frameworks offer different perspectives, all of which might capture something true while none captures everything. You can appreciate that the linguistic categories you use are tools, useful but not inevitable, one way among many of carving up the continuous flux of experience into manageable, thinkable, communicable units. As you rest now, the language centers in your brain begin to quiet. The constant inner monologue, the linguistic interpretation of experience, starts to fade. What remains is more direct, more sensory, less categorized. The breath is just the breath, not my breathing or good breathing or I should breathe more deeply. The body sensations are just sensations, not tension in shoulders or tiredness or need to shift position. This prelinguistic awareness, this dropping of conceptual filters, is deeply restful, allowing the language processing parts of your brain to rest, to stop their constant work of labeling and categorizing and narrating, and simply let experience be what it is. Consciousness and the mystery of awareness. Consciousness remains one of the deepest mysteries in all of science. How does the physical brain, this 3-pound lump of cells and electrical activity, give rise to subjective experience, to the feeling of what it's like to be you? How do billions of neurons firing in patterns create the sensation of seeing red, the taste of chocolate, the experience of joy or sorrow? This is sometimes called the hard problem of consciousness, distinguishing it from the easy problems of explaining specific cognitive functions like memory or attention. The hard problem is explaining why there's any subjective experience at all, why it feels like something to be conscious. Philosophers have debated consciousness for millennia. Neuroscientists have made enormous progress mapping the neural correlates of consciousness, identifying which brain activity accompanies which conscious experiences. But the gap between objective description of neural activity and subjective experience remains. You can know everything about the neurons firing in someone's visual cortex when they see red, but that knowledge doesn't capture what red looks like from the inside, the qualitative character of the experience itself. Consciousness has multiple dimensions. There's wakefulness, the basic state of being awake versus asleep or unconscious. There's awareness, the ability to have conscious experiences, to perceive and feel. And there's content, the specific things you're conscious of at any moment. These can vary independently. In vegetative states, people may be awake, eyes open, sleep-wake cycles present, but without awareness or content. In dreams, you have awareness and rich content, but not the same wakefulness as during normal waking. The neuroscientist Francis Crick, who earlier helped discover DNA's structure, devoted his later years to consciousness research. He proposed that instead of trying to solve the hard problem directly, scientists should focus on the neural correlates of consciousness. What specific patterns of brain activity correlate with specific conscious experiences? If we can map these correlates precisely enough, we might understand the mechanisms that support consciousness, even if we can't yet explain why those mechanisms produce subjective experience. This approach has been productive. Researchers have identified brain areas that seem particularly important for consciousness. Damage to certain areas, like the thalamus or connections between thalamus and cortex, can eliminate consciousness even when most of the brain remains intact. This suggests that consciousness depends on specific circuits, not just on having a functioning brain generally. The global workspace theory, proposed by Bernard Bars and further developed by others, suggests that consciousness arises when information becomes widely broadcast across the brain. Most processing happens locally, in specific modules that aren't directly accessible to consciousness. But when information enters a global workspace, a network that distributes it widely across many brain areas, that information becomes conscious. Attention is the mechanism that selects what enters the workspace. What you're conscious of is what's currently in the global workspace, accessible to many systems for reasoning, memory, action planning. Another influential theory, integrated information theory developed by Giulio Tononi, proposes that consciousness corresponds to integrated information, the degree to which a system unifies information in a way that cannot be reduced to independent parts. High integrated information means the system's current state is determined by many interdependent elements, creating rich structure that cannot be captured by looking at the parts separately. Tononi has even proposed a mathematical measure of integrated information, called phi, which in principle could be calculated for any physical system to determine its level of consciousness. These theories make different predictions and emphasize different aspects of consciousness. Global workspace focuses on broadcasting and access. Integrated information focuses on unity and irreducibility. Neither has been conclusively proven, and both face challenges. But both represent serious attempts to bridge the gap between neural mechanisms and conscious experience. Recent research has highlighted the role of brain rhythms and oscillations in consciousness. During wakefulness, the cortex produces relatively fast, desynchronized activity. Different areas oscillate at different frequencies, with complex patterns of synchronization and desynchronization. During deep sleep, slower synchronized oscillations dominate. During REM sleep, activity speeds up again, resembling wakefulness in some ways. These rhythms might be crucial for creating consciousness. Synchronized oscillations can bind together activity in distant brain areas, creating temporary coalitions of neurons that process different aspects of the same object or event. The synchronized activity might be what allows distributed information to be integrated into a unified experience. You don't experience separate color, shape, and motion. You experience a unified red ball rolling across the floor. That unity might emerge from synchronized oscillations binding together neurons processing color, shape, and motion. Some researchers have proposed that consciousness involves not just activity in specific areas or networks, but rather waves of activity propagating through the cortex. These traveling waves create spatial and temporal patterns that might encode conscious content. The brain is not a static processor but a dynamic system with wave-like activity creating constantly shifting patterns across its surface. There's also growing interest in electromagnetic fields as potentially relevant to consciousness. Every neuron firing creates tiny electrical and magnetic fields. When many neurons fire together, as they do constantly in the cortex, they create measurable electromagnetic fields. Could these fields, rather than or in addition to the discrete spikes of individual neurons, play a role in consciousness? This might sound far-fetched, but there are theoretical reasons to take it seriously. Electromagnetic fields can influence neural activity through what's called a phaptic coupling, where the field from one group of neurons affects nearby neurons without direct synaptic connections. This creates a form of communication that's much faster than synaptic transmission and operates at a larger scale. Some researchers speculate that conscious experience might correspond to these field effects, which would explain why consciousness seems unified and holistic rather than simply a collection of discrete neural spikes. The boundaries of consciousness are unclear. When you're under general anesthesia, you're unconscious, but some neural processing continues. Information still reaches your brain. It's processed to some degree, but it doesn't become conscious. The anesthesia disrupts the thalamocortical communication necessary for information to reach global broadcast or achieve high integration. Similarly, in deep sleep, your brain is very active, but most of that activity doesn't create conscious experience. There are intriguing edge cases. Split-brain patients, whose corpus callosum connecting the two hemispheres has been severed to treat epilepsy, sometimes show behaviors suggesting each hemisphere has its own separate consciousness. Visual information shown to only the left hemisphere can be reported verbally, since language is usually in the left hemisphere. But information shown to only the right hemisphere cannot be verbally reported, though the patient can point to it with their left hand, controlled by the right hemisphere. Does each hemisphere have its own awareness, its own stream of consciousness? The question is unresolved, but it suggests consciousness might be more divisible than it seems from the inside. Disorders of consciousness present profound challenges. Patients in persistent vegetative states may be awake but show no signs of awareness, no response to stimuli that suggests conscious experience. But recent neuroimaging studies have revealed that some patients diagnosed as vegetative actually have preserved consciousness. When asked to imagine playing tennis or walking through their house, their brain activity shows the expected patterns, even though they can't move or speak to report their experience. These are truly islands of awareness, conscious minds trapped in unresponsive bodies. Locked-in syndrome, usually caused by brainstem damage that paralyzes all voluntary muscles except eye movements, leaves patients fully conscious but unable to move or speak. Before eye-tracking technology allowed communication, these patients were sometimes mistaken for unconscious. The thought of being fully aware, fully conscious, but completely unable to communicate that consciousness is terrifying. It illustrates how fragile the connection is between internal experience and external expression. These cases highlight something important. Consciousness itself is not directly observable. You can never know for certain whether another entity is conscious. You infer consciousness in other humans from their behavior, from their reports, from the similarity of their brains to your own. But the inference could be wrong in either direction. You might think someone is unconscious when they're actually aware, as with some vegetative patients. You might attribute consciousness to entities that lack it, a philosophical possibility some raise about sophisticated AI systems that behave intelligently but might lack inner experience. You know with absolute certainty only that you yourself are conscious. This is Descartes' famous, "I think, therefore I am," the one thing you cannot doubt. Everything else, including the consciousness of everyone you've ever met, is an inference based on evidence and assumption. This might seem solipsistic or depressing, but it's actually just an honest recognition of what consciousness is. A private, subjective phenomenon accessible directly only to the one experiencing it. Yet, despite this privacy, there's something universal about consciousness. Every conscious being, presumably, has the sense of being a subject of experience, of there being something it's like to be them. The specific contents differ. What it's like to be you is different from what it's like to be anyone else. different even from what it was like to be you a moment ago as new experiences arise and fade. But the basic fact of being a conscious subject, of having an inner perspective on the world, seems to be shared. Some philosophers and contemplatives suggest that beneath the constantly changing content of consciousness, there's a bare awareness that remains constant. You can notice this in meditation. Thoughts come and go, sensations arise and pass, but the awareness of these changing phenomena seems somehow constant, unchanging, the stable background against which all experience plays out. This bare awareness is sometimes called consciousness without content or pure awareness, and traditions like Buddhism and Advaita Vedanta place great emphasis on recognizing and resting in it. From a neuroscience perspective, this might correspond to the activity of certain networks when they're not engaged with specific content. The default mode network might create the sense of self, the I, that seems to persist across experiences. When this network quiets, as in deep meditation, the sense of a separate self might dissolve, leaving only the awareness itself. This is described as profoundly peaceful, a recognition that you are not just your thoughts, emotions, and sensations, but the awareness in which all of these appear. Understanding consciousness as emerging from neural activity doesn't diminish it. You are not just neurons firing. You are the process, the activity, the patterns of information integration and global broadcasting and synchronized oscillations that constitute conscious experience. To understand that consciousness is a natural phenomenon, arising from physical processes, is not reductive. It's wondrous. The universe has arranged matter in such a way that it becomes aware of itself. In you, the cosmos has achieved self-awareness, however briefly, however imperfectly. As you drift now toward sleep, your consciousness will shift through various states. The clear, bright awareness of wakefulness will give way to the hypnagogic state, that twilight zone between waking and sleeping where thoughts become dreamlike, logic loosens, images arise unbidden. Then consciousness will fragment as you enter light sleep, awareness flickering in and out. In deep sleep, conscious experience may cease entirely, or it may continue in a way you won't remember. In REM, consciousness will return in the strange, vivid form of dreams. Throughout all of this, your brain will continue its ceaseless activity, creating consciousness when conditions are right, letting it subside when they're not. And in the morning, consciousness will reassemble itself, will boot up again, and you'll wake with that fundamental sense of being aware, of being here, of being you. The mystery of how this happens remains. But the fact that it happens reliably, every day, billions of times across all conscious beings on Earth, is perhaps the most profound and peaceful fact of all. The calming science of now living with our filtered reality. Understanding how your brain filters reality, how it constructs your experience from predictions and limited sensory input, how consciousness emerges from neural activity. All of this knowledge has practical implications for how you live, how you relate to your experience, how you find peace in an overwhelming world. The neuroscience of perception and consciousness isn't just abstract theory. It's deeply relevant to the question of how to live well, how to suffer less, how to be present and at ease. First, recognizing that your brain filters reality aggressively can reduce the pressure to process everything. You don't need to read every article, respond to every email, notice every detail. Your brain is already selecting ruthlessly what gets your conscious attention. You can work with this natural filtering by being intentional about what you expose yourself to and what you give your attention to. If you're constantly bombarded with news, notifications, demands, your RAS stays in high alert mode, treating everything as potentially urgent. This is exhausting, creating periods of lower stimulation. Turning off notifications, spending time in nature, reducing information consumption allows your RAS to relax. You're not missing out. You're allowing your brain's filtering systems to work more effectively by reducing the total volume of input they must process. Mindfulness practices work partly by training attention, which in turn trains the RAS. When you practice noticing your breath or sounds or body sensations, you're teaching your RAS that these stimuli are important. Over time, this makes you more aware of present-moment sensory experience and less caught up in mental chatter. You're reprogramming your filters to let through different information. There's a practice called the 5-4-3-2-1 technique that directly works with sensory awareness. Notice 5 things you can see, 4 things you can touch, 3 things you can hear, 2 things you can smell, and 1 thing you can taste. This forces your attention to cycle through different sensory modalities, activating channels that are usually filtered out when you're lost in thought. It's grounding, calming, a way of bringing your attention into direct sensory experience rather than abstract mental content. Active meditation or mindfulness in daily activities extends this principle. When you eat, actually taste the food rather than eating while distracted. When you walk, feel your feet on the ground, notice your body moving through space. When you shower, feel the water on your skin. This isn't complicated. It's just directing attention to present sensory experience, which is already happening but usually filtered from consciousness because you're focused on thoughts about past or future. This relates to the predictive nature of perception. Your brain is constantly predicting what will happen next, often based on past experiences. If you've showered 1,000 times, your brain has strong predictions about what showering feels like, and it doesn't need much actual sensory information to confirm those predictions. The experience can become almost entirely predicted, barely consciously registered. But if you intentionally attend to the sensations, you can override those predictions, forcing your brain to actually process the sensory information rather than just confirming predictions and moving on. This makes experiences richer, more vivid. Routine activities that have become dulled through repetition can become interesting again when you bring attention to them. This is not about forcing yourself to enjoy everything or being annoyingly positive. It's simply about reducing the gap between experience and awareness of experience, about living with less filtering, more direct contact with what's actually happening. Understanding that your brain makes predictions that shape experience also opens up possibilities for working with those predictions. If you predict a situation will be threatening, your brain will construct a threatening experience, highlighting dangers and missing safety cues. Your body will respond with stress hormones, your RAS will become hypervigilant, and the situation will feel threatening even if it's objectively safe. But if you can shift the prediction through cognitive reframing, through exposure that allows new learning, through practices that calm your nervous system, the same situation can feel completely different. This is the basis of exposure therapy for anxiety. When you avoid situations you fear, your brain never gets evidence that they're safe. The predictions remain unchallenged. The anxiety persists. But when you approach the feared situation, ideally in a graduated way that doesn't overwhelm you, your brain gets prediction errors. I predicted catastrophe, but I'm okay. These prediction errors update your model. The predictions shift. The next time, the situation feels less threatening. Gradually, through repeated exposure, your brain learns that its catastrophic predictions were wrong, and new, more accurate predictions replace them. You can use this understanding to work with difficult emotions. When you feel anxious, sad, or angry, there's often a predictive component. Your brain is predicting something bad will happen, that you'll lose something valuable, that you've been wronged. These predictions generate the emotion, but predictions can be questioned. Is the prediction accurate? What evidence supports it? What evidence contradicts it? Often, examining predictions consciously can reveal that they're based more on past patterns than on current reality. This doesn't make emotions disappear or invalidate them. Emotions provide valuable information, even when they're based on inaccurate predictions. But creating some space around them, recognizing them as your brain's predictions rather than direct readouts of reality, can reduce their overwhelming quality. You can feel anxiety without being completely consumed by it, feel sadness without drowning in it, feel anger without being controlled by it. Practices that calm the nervous system, deep breathing, progressive muscle relaxation, yoga, tai chi, work partly by changing your brain's predictions. When your body is in a state of physiological calm, when your heart rate is slow, your muscles relaxed, you're breathing deep, your brain predicts safety. This shifts the filtering. Threat cues are less likely to break through to consciousness. Neutral stimuli are less likely to be interpreted as threatening. The same environment becomes less stressful simply because your body state has changed, which has changed your brain's predictions. The RAS is particularly responsive to this. In states of chronic stress, the RAS becomes hypersensitive, treating everything as potentially urgent. This is appropriate in genuinely dangerous situations, but when it becomes chronic, it's exhausting and counterproductive. Calming practices can retrain the RAS to be less reactive, to filter more selectively, to allow rest. Sleep, which we discussed earlier, is crucial here. When you're sleep-deprived, your RAS doesn't function properly. You become both more reactive to stimuli, because your brain can't effectively filter, and less able to focus, because you can't sustain attention. Getting adequate sleep is not just about feeling rested. It's about maintaining the neural systems that filter your reality, keeping them functioning properly so they can protect you from overwhelm. Recognizing that reality is constructed, that what you experience is your brain's prediction more than a direct readout of what's out there, can cultivate a certain flexibility. You might hold your interpretations more lightly, recognizing that they're provisional, based on limited information and potentially biased by past experience. This doesn't mean abandoning all judgment or becoming paralyzed by uncertainty. It means staying open to updating your models when new evidence arrives, being willing to revise beliefs when predictions are repeatedly contradicted. This is particularly valuable in relationships. When you interpret someone's behavior, you're bringing massive amounts of prediction to bear. You're predicting their intentions, their emotions, their thoughts about you. These predictions are based on your past experiences with them and with others, your current emotional state, your own insecurities and hopes. They might be accurate or they might be wildly wrong. Recognizing that your interpretation is a prediction rather than a fact can create space for communication, for checking assumptions, for being open to alternative explanations. The same applies to your interpretation of yourself. The story you tell about who you are, why you do things, what you're capable of, this is all prediction. Some of it is well supported by evidence. Some of it is habit, repetition of what you've always believed about yourself without much critical examination. You have more capacity for change than you might think, precisely because much of what you take as fixed truth about yourself is actually prediction, and predictions can be updated. Understanding that consciousness itself is a constructed phenomenon, emerging from brain activity rather than being a separate soul or essence, might initially seem depressing or reductive. But many people find it actually quite liberating. It means you're not stuck with the consciousness you have. Can change. When your brain changes through learning, through healing, through deliberate practice, your consciousness changes too. It also means there's no separate you that's broken or defective, no essential self that needs fixing. There are just patterns of neural activity, some of which create suffering, some of which create well-being. Those patterns can change. You can be gentle with yourself, recognizing that what you experience as failings or flaws are really just how your brain happens to be functioning right now based on its history and current state, not immutable truths about your essential nature. The contemplative traditions have understood this for millennia, even without modern neuroscience. The Buddhist concept of non-self, for instance, teaches that what we take to be a solid, continuous self is actually a process, a constantly changing flow of experience without a fixed, unchanging essence at its core. Neuroscience is arriving at similar conclusions through different methods. The self is a construction, an ongoing process of neural activity, not a thing. This doesn't make your experience less real or less important. Your suffering is real. Your joys are real. Your relationships matter. But recognizing the constructed, process-based nature of selfhood can reduce the clinging, the desperate attempt to preserve and protect a self that was never as solid as it seemed. There's freedom in this recognition. As you move towards sleep now, you can let all of this knowledge settle. Your brain will continue its filtering, constructing your reality from sensory fragments and predictions, creating the experience of you. But you can rest in the recognition that this is all working exactly as it should, that your brain's sophisticated filtering systems are protecting you, that consciousness will return in the morning, that all of this complexity and mystery is somehow giving rise to this moment of peaceful awareness, this gentle drift into restorative sleep. You don't have to understand it all. You don't have to control it. Your brain has been doing this for your entire life, and it will continue. The filtering will happen. The predictions will be made. Consciousness will ebb and flow through its various states. And through it all, there's this underlying capacity for awareness, for knowing you're experiencing, even as the content of experience constantly changes. Rest now in that awareness. Let the filters do their work. Let the predictions run. Let consciousness shift and change as it will. You are safe, held by billions of years of evolution that crafted this extraordinary brain, this remarkable filtering system, this generator of consciousness that allows you to be here, to know you're here, to peacefully drift now into the restorative darkness of sleep. The gift of filtered awareness. As we come to the end of this journey through the neuroscience of filtered reality, take a moment to appreciate the extraordinary gift of your filtered awareness. Your brain processes 11 million bits of information each second but shows you only 40 to 50, creating a manageable, navigable world from an overwhelming universe. It builds predictions from your lifetime of experience and uses those to construct your perceptual reality, usually accurately, always protectively. It cycles through consciousness states, waking, sleeping, dreaming, each serving essential functions for your survival and well-being. You are not a passive observer of reality. You are an active participant in its construction, your brain constantly predicting, filtering, interpreting, creating the experience of being you in the world. This is not a limitation. This is wisdom, protection, mercy. Without these filters, you would be paralyzed by overwhelm, unable to focus, unable to function. With them, you can live, love, learn, grow, experience peace even in a chaotic universe. Sleep well, knowing your brain is working for you, filtering reality, maintaining consciousness, preparing for tomorrow's experiences. And when you wake, you'll once again experience the miracle of filtered awareness, the extraordinary construction of reality that is your everyday experience, the peaceful power of a brain that knows exactly what you need to know and protects you from the rest. If you enjoyed this journey into the peaceful science of the brain, please like this video and subscribe to Deep Science Sleep for more calming explorations of neuroscience and the mysteries of consciousness. Until next time, rest well in your beautifully filtered reality.